So today I am going to talk about isospin. I divided this lecture into two parts. So in the first part I will talk about concept of spin. First part is where I will talk about concept of spin. Sorry, not spin but isospin. And in the second part I will talk about the algebra of isospin. Right, these are the two parts which I will talk about in this lecture. So let me talk about that how the idea of isospin came. So as we know that concept of isospin. So for this consider the electrons, consider protons and neutrons. Let us have a look at their masses. So mass of proton is equal to 1.67262192 into 10 raised to power minus 27 kg, whereas the mass of neutron can be written as 1.674947 into 10 raised to power minus 27 kg. So these are their masses and they are slightly different. Another thing regarding neutrons and protons is that nuclear force is responsible for stability of nucleus. Right, stability of nucleus, and this nuclear force is independent of charge. This nuclear force is independent of charge. So in other words, we can say that strong force potential is same for all nucleon pair. Almost same for all nucleon pair. That means potential between proton and proton is nearly equal to potential between neutron and proton and potential between neutron and neutron. So Heisenberg, keeping all these things in mind, Heisenberg suggested that if we switch off electric charge of proton, then we cannot distinguish between proton and neutron, right? We cannot distinguish between proton and neutron. So keeping this in mind, keeping this in mind, it was proposed that neutron and protons are true states of single entity, right? Single entity, and it is analogous to, which is analogous to spin up and spin down, states of spin half particles. So that means proton is represented by 1 0 state and neutron is 0 1, and this leads to introduce the concept of isospin, that means protons and neutrons, protons and neutrons form protons and neutron form isospin doublet, and this is similar to spin with total isospin I equal to 1 by 2, and third component of isospin that is I3 is equal to plus minus 1 by 2 for the proton and the neutron. So charge independence of and important thing is that the charge, this is a very important point, charge independence of strong nuclear force is then expressed in terms of invariance under unitary transformation. Under unitary transformation in the form of isospin space. In this isospin space, right? Isospin satisfies, another important thing is that isospin satisfies SU2 algebra. SU2 algebra. This is similar to spin. This is similar to spin. Physically, isospin has nothing to do with the spin. Has nothing to do with spin, right? Now let us talk about the algebra of isospin. Algebra of isospin. Like ordinary angular momentum, as we know that in case of angular momenta, we have defined some rules. So like ordinary angular momentum, we introduce a quantity. Isospin I having three component I1, I2 and I3 in isospin space. In isospin space, the operator I satisfies the commutation relation of angular momentum J. So keeping in mind the results of angular momentum, let us define raising and lowering operator for isospin space. So I call it as I plus is equal to I1 plus iota I2, and similarly I can define I minus is equal to I1 minus I plus minus iota I2. This is called raising operator, and we call it as the lowering operator, as we have defined for the case of the angular momenta. Also it's similar to that. And matrix elements of so all these operators regarding angular momenta I talked about in the lectures of the quantum mechanics, so you should go through that. So the matrix elements of four isospin operators, that is I2, I3, I plus and I minus with respect to I comma I3 as a basis are given by so First is that is I3 I square I3 means expectation value of I square when operated with I and I3, it can be I into I plus 1 delta I3 prime, right? Or in some text it can be written as I square I3, it can be written as I into I plus 1 I3, right? So one and same thing. Then second is I3 its prime, it is I3, it is I3, so it is I3 as it is, means eigenvalue of this I3 is I3, the eigenvalue of I square when operated with this I and I3, then it is I into I plus 1, so its eigenvalue will be this one and its eigenvalue will be this one, so it is I3, sorry, it is delta I3 prime, or we can write it as, either we can write down it in this way, or another way is this, that I3 is equal to I3 I3, right? And third is a very important thing which we have to keep in mind. This is very important. Let me write down that. So it is I comma I3 prime I plus minus for letter operators, this relation is I3 plus minus 1, it must be equal to I into I plus 1 minus I3 plus minus 1 whole under the root into delta I3 plus minus 1, or it can be also be written in some text as I plus minus I3 is equal to I into I plus minus 1 minus I3 plus minus 1 whole under the root and multiplied by get I3 plus minus 1. So that's it, right? These are the few relationship which we have to keep in mind. The fundamental two-dimensional representation of the fundamental the two-dimensional representation of isospin rotation group is based on three matrices. That is top one, it is 0 1 1 0, and these are similar to polyspin matrices, right? So 0 minus iota 0 dot 3 is equal to 1 0 0 minus 1, so which are identical to polyspin matrices. which are identical to polyspin matrices. Also, II can be written as 1 by 2 tau I, such that tau I by 2, their commutator, it is J, tau J by 2, its commutator is equal to I epsilon I j k tau k by 2. And keeping this in mind, we can write down it as I j, its commutator is equal to epsilon I j k I k, right? Also, I3 has 2I plus 1 eigenstates, that is minus I2 and so on plus I in a step of 1. Possible eigenvalues of I are they are either 0, 1 by 2, 1, 3 by 2 and 2 and so. So for proton, let me talk about this for the proton and then pion. So for proton and for neutron, let us talk about it. For proton is represented by P, ket P, so it has, these are the values of the isospin, total isospin and its Z component. So it is 1 by 2 and 1 by 2 for the proton, but whereas for neutron it is 1 by 2 and minus 1 by 2. And similarly for pion, pions II3 get II3 are given as, let me write down. So for pi plus or pi naught or pi minus, we can write down the value of this state factor. It is 1 1, it is 1 0, or it is 1 minus 1, right? Also we can define charge operator that is Q is equal to EI3 in terms of spin, right? It can be defined like this. So where E is the, here E is charge on proton. So let us talk about proton. So when Q operator operates over P, it is equal to E, because its value will be I3 plus 1 by 2. The proton value will remain as it is, but for proton I3 is 1 by 2, so 1 by 2 plus 1 by 2, so it is simply P multiplied by E. Also for the neutron, we can do it like this. So it is EI3 plus 1 by 2, but for neutron I3 is equal to minus 1 by 2. E, it is neutron, right? So it is simply 0, right? So thus the concept of isospin also explain the charge on proton and neutron. Means concept of isospin also explain charge on nucleons, right? So that's all for this lecture.